You know when you're just kind of doodling, coloring in a map? Maybe it's a map of the world, maybe it's just some random shapes you drew. Have you ever noticed that you seem to only need a few crayons to make sure no two touching countries are the same color? Well, that simple little observation is actually the doorway to one of the most notorious and difficult problems in the entire history of mathematics.
So, let's get right to it. The big question is this. Can any map you can possibly dream up, no matter how complicated, be colored with just 4 colors? That's it. That's the whole puzzle. It sounds like something you'd find in a kid's coloring book, right?
But yeah, no. This little puzzle, it absolutely tormented the world's best mathematicians for over 120 years. It became this legendary obsession that embarrassed some of the greatest minds out there, and in the end, it actually changed how we think about what a mathematical proof even is.
So to really get why this was so tough, we gotta lay down the ground rules. What do we actually mean when we talk about coloring a map? There are some very specific details we need to get straight.
Okay, so here's the official fancy way of saying it. The four-color theorem states that for any map you can draw on a flat surface, you will never, ever need a fifth color to do the job, as long as no two neighbors have the same color.
Now this right here is the #1 rule of the game, the one that trips everyone up. Adjacent means two regions have to share an actual border, a line. They can't just touch at a single corner. Think about the 4 corners in the US, where Utah, Colorado, Arizona, and New Mexico all meet at one tiny point. In this puzzle, they don't count as being adjacent to each other. That little distinction is everything.
And to make this a real math problem, you got to get rid of the messy stuff like actual maps. What mathematicians do is turn the map into something called a graph. Every country or region becomes a dot, and you draw a line connecting any 2 dots that share a border. The question then becomes, can you color the dots of any of these planar graphs with 4 colors so that no 2 connected dots are the same?
All right, so we've got the rules. Now, let's dive into the history, because it is a long and frankly pretty frustrating story of near misses and epic failures. It's a real mathematical mystery.
So check this out. The question is first asked way back in 1852. Then crickets for decades. Finally, in 1879, a guy named Alfred Kemp publishes a proof and everyone celebrates. Problem solved. Except, 11 years later, someone found a mistake, a fatal flaw. The puzzle was back on. And it would stay that way all the way until 1976.
I mean, just let that sink in for a second. For 2 separate periods, each lasting more than 10 years, the entire mathematical community thought this thing was done and dusted. The fact that 2 different proofs, accepted by the absolute best minds of the time, turned out to be wrong, that just shows you how incredibly deep and sneaky this problem really was.
So after 100 years of human brainpower just hitting a wall, the solution came from a place nobody really expected. This is where the machine enters the story, and this is where things get really, really weird.
The strategy that 2 mathematicians, Kenneth Appel and Wolfgang Haken, came up with was super clever. It's called proof by contradiction. They started off by saying, okay, let's just pretend for a minute that a map that needs 5 colors actually exists. They wanted to prove that this idea leads to an impossible contradiction. Their logic was that any such map had to contain one of a specific list of shapes. But then, they showed that every single one of those shapes could be simplified in a way that meant the map didn't need 5 colors. So a map that needs 5 colors must contain a shape that proves it doesn't need 5 colors. It's a total contradiction, which means the 5-color map can't exist to begin with.
So how many of those unavoidable shapes did they have to check to make their proof work? Was it 10? 100? Nope. 1,834. That's how many different map configurations they had to check, one by one. It was a number so huge that no human, or even a team of humans, could ever hope to get through it.
And that is why they needed a computer. They wrote a program to just brute force its way through all 1,834 cases. It took over 1,000 hours on a 1970s supercomputer. When the last line of code ran and the computer confirmed every single case worked, the proof was finally complete. The 4-color theorem was true.
But here's the thing. When they announced they'd done it, not everyone started cheering. In fact, it kicked off this huge, almost philosophical argument that totally split the math world right down the middle.
And it all came down to this one really unsettling question. Is a proof really a proof if a human being can't actually check it? For all of history, a proof was an argument that a person could read, understand, and verify. This was different.
This was a black box. The computer just spit out the answer. True. But how could you be sure? Was this even math anymore?
This quote from the mathematician Ian Stewart just nails the feeling a lot of people had. Great mathematical proofs are supposed to be elegant, beautiful. They give you a deep insight into why something is true. This computer proof, it felt like a brute force beatdown. There was no insight, no beauty. It just was.
But over the years, the proof has gotten a lot more solid. First, the number of cases was whittled down to 633, still way too many for a person, but better. And then the real kicker. In 2005, a completely different team with completely different software formally verified the entire logical argument. So now, yeah, any doubts about the computer's original calculation are pretty much gone. It's accepted.
Okay, so the theorem is proven. Case closed. You'd think mapmakers would be throwing parties, right? Well, not exactly. The story takes a few more weird turns, and we're about to go way beyond flat maps.
See, the funny thing is, for actual cartographers, this whole thing is kind of a fun fact, but not much more. For one, it doesn't work for places like Alaska and the rest of the US because they aren't connected. And honestly, in the real world, you can almost always get by with just 3 colors. It's pretty rare you even need a 4th.
But this is where things get really mind-bending. What if your map isn't on a flat piece of paper? What if you drew it on, say, the surface of a donut? Well, on a donut, a torus, it's possible to draw a map that needs 7 colors. 7! And on this other bizarre shape called a Klein bottle, you'd need 6. The actual shape of the surface your map lives on completely changes the rules of the game.
And then if you try to go from 2D to 3D, the whole thing just goes off the rails. It's actually pretty easy to arrange a bunch of 3D objects so that every single one is touching every single other one. In that case, how many colors do you need? You'd need an infinite number. So this whole 4-color thing, it is strictly a flat world phenomenon.
So when you look back at the whole journey, the 4-color theorem is about so much more than coloring in some shapes. It's really a story about the limits of human genius, the beginning of a new kind of partnership with machines, and how a question a child could ask can have an answer so complex it pushes the very boundaries of what it means to know something.
And that leaves us with this really exciting thought, doesn't it? It took 100 years of failure, and then a brand new tool, the computer, to finally crack this one simple puzzle. So you have to wonder, what other simple questions are out there right now just waiting for us to invent the next new way to think about them?